Our third speaker is Christoph Bürgstaller. He is the Managing Director and Head of Research at the Transfer Center für Kunststofftechnik TCKT in Wels, Austria since 2015, as well as full professor for plastics engineering at the Upper Austria University of Applied Sciences since 2021. His background is in chemical engineering, and he has been involved in application-oriented research in the plastics technology sector. His work deals with structural processing property relationships of thermoplastic materials in general, with the main focus on composites and blends, as well as recycling.
Yeah, welcome everybody. I have the honor to present the PLASTICE project, or PLASTICE project, where we are working on different aspects of what to do with waste plastics and keep the plastics in the loop. I have a short image video I want to play.
Earth has been experiencing a major environmental issue. Oceans, forests, beaches, and all natural habitats are affected by an abundance of plastic litter. But plastics could be recycled more and better. With new technologies, plastic landfill stands to be cut significantly. One option is the valorization of the materials into new feedstocks, and that's where the new EU project, PLASTICE, comes in, closing the loop in the plastic life cycle. PLASTICE strives to apply valorization processes aligned with the latest chemical conversion technologies in 4 countries: Austria, Italy, Spain, and the Netherlands. 4 conversion technologies will be developed at these demos, from lab scale up to real environment prototypes. Microwave-assisted pyrolysis, hydrothermal liquefaction of polyolefins, combined gasification and chemical post-treatment, and cascade enzymatic hydrolysis. These technologies aim to reduce greenhouse gas emissions by 70% overall. Learn more at plastice.eu.
So with that, we have set the stage so I can explain a little bit what we are doing in PLASTICE. We are a rather large consortium, and we have different routes, as pointed out in the presentation, where we want to use the plastic waste which is collected and sorted, and where we have different fractions. For example, we have different plastic materials where we want to use our microwave-assisted pyrolysis or the hydrothermal liquefaction to go back to pyrolysis oil. The second thing we're doing is to take the solid recovered fuels and by the combined gasification and chemical treatment, we want to go back to olefins and dimethylator. And the third one is maybe a little bit the odd one out here in this setting because we don't put the material up to high temperatures, but we use textiles, mixed textiles. We are also a reasonable large component is plastics, and we use an enzymatic treatment to separate polyester fibers from glucose. Yeah, what are the objectives in our project? The first one is to, as it's about demonstration, to develop new plastic valorization processes and to also demonstrate them at a reasonable scale, especially for these unsortable or unsorted or low valorization materials for plastics and the textile waste, because there is a reasonable share of plastics in that. The second one is to obtain products which are ready to feed into downstream processes for the further production again of polymers, as we showed before. The third is to reduce the carbon footprint of the current chemical recycling processes, especially for the fractions which cannot be mechanically recycled. And the one there's the animation messed up. We also want to establish the roadmap for the implementation of our solutions into the industrial realities and regions, tackling the technical and non-technical barriers. And yeah, sometimes you really get non-technical barriers while such a short project. And the third is to ensure the successful dissemination and exploitation of the product. So we're also looking into the business models. Can this be feasible or not? Our 4 demo sites are shown here. We have 2 demo sites in Spain, We have one in Italy and one in Austria, where we deal with the different technologies. And I will show you in the next slides what we are doing there and what's the current status of that. First one, the microwave, sorry, the microwave-assisted pyrolysis. Yeah, we see this as an environmental friendly alternative to incineration, and especially to inefficient landfilling. We want to produce, again, as a similar approach as in your projects. We want to have a liquid that then can be further refined. And with this municipal plastic waste, with the microwave pyrolysis, we get the chance that when we pyrolyze the material, as in all pyrolysis processes, that we don't have an issue with some legacy additives or something like that. Also, we want to apply this to a wide range of feedstock, and we see this as a quite feasible and also economical alternative for mixed plastic wastes. So what are we doing there? What's the basis of that? We basically use microwaves as we use at home in your kitchen, but at a little bit larger energy, between 300 megahertz and 300 gigahertz, and we use that to bring the energy into the mixture. Not only the plastics alone, that wouldn't work. So we need some catalysts. We need some stuff which is susceptible to the microwaves, and with that we can heat up the material very, very rapidly. And you can see here on the right hand side two let's say pictures of how such a vessel could be heated up. If you do the conventional heating, plastics have the large drawback or the advantage of having very poor thermal conductivity. And what we, when you heat it up from the outside with conventional heating, you just need a very long time until it's molten on the inside or it's hot enough on the inside. With the microwave heating, as the microwaves can penetrate the material much better, we heat it up from the inside, and with that we get a very nice rapid heating. And due to the low thermal conductivity of the plastic, we have the chance, we have the insulation around, so it stays also rather hot. What's the status of that? Here you can see the prototype or demo setup at the Spanish site at Sirces. Sirces is also the coordinator of the project. You can see here such a microwave reactor. It's a continuous microwave reactor concept. Basically, the start was first a small, let's say, tube-shaped reactor where the material was fed in. The microwaves are penetrating, and now they set it up at the larger scale with this pilot plant. So that's the current status of that. That's currently running. They're currently being optimized, and the major input they're currently looking at is the LDPE-based waste. So that is quite nicely working, and that can really give you pyrolysis oil and solid carbon and gases, similar, as I said, to your technologies you presented before. The next one is the hydrothermal liquefaction. That's a bit of another process. So what we aim there is, again, the process was originally developed for converting biomass, and here what we are doing is we use hot water at very high temperatures at near or supercritical conditions to degrade the plastic. So here we have a single fluid phase then, and with this single fluid phase we can run the reactions. One advantage of that is that there is no need of a high energy consuming drying step, and the HDL is also rather capable of treating really different feedstocks and different wastes. What's the status there? You can see here different feedstocks. We have the let's say pre-cleaned HDPE and LDPE, but we also have this SRF fraction. And basically what we have here, we feed the waste into the HDL reactor with water and heat it up rapidly to very high temperatures, and then we get different products out. You see there are the percentages given. I don't have my reading glasses with me, so we have a gas fraction up to 40%. We have an oil fraction between 30 and 80%, and then we have the char. What exactly comes out is depending a lot on the input, naturally. So if you have already a high inorganic content in your plastic waste, and this will go to the jar naturally. And it also depends a little bit on what other materials you have in there. If you stick to polyolefins, it's quite nice. If you have some PVC contaminations, that is an issue we need to deal with. So what is currently going on? Currently, the pilot scale reactor of this hydrothermal liquefaction is produced. You can see here this setup. So we would have a 25-liter reactor to run the trials and to get better insight on how to run the process. The next process is, I need to speed up a little bit maybe, the next process is the gasification of plastic waste. That's the third, let's say, technology we work on that. So we start from these secondary fuels, and then we do a conversion, a gasification conversion at very high temperatures of 900 degrees C, where we do pyrolysis, oxidation, and reduction in these 3 steps. And what we're aiming for like products like DME, which then can be used as a fuel or as a feedstock again. So what we can see here is we have different fractions in there, and there is let's say a small pilot going on where we have the gasification reactor. I only can show you this cutout scheme. We have a plastic feeding system. Similar as we saw today in the tour. Somehow you need to bring the feeding. You need to feed the plastic material in. Then the gas injection system, and then we have the syngas treating system and the syngas analyzer at the end here in our setup. To give you an idea, what do we get when we put in the dried SRF and the air we get of major product is gas, as it's a gasification process. There are some solids and some ashes, and it's about around 5 to 8%, if I remember correctly, where there is still valorization pending at the current state. We know of that. And where are we currently? So there are currently trials running on the catalytic conversion. So this process again is built up, and to look into how to convert the syngas to DME. The last one is, as I said, the odd one out. That's where I'm mainly working, so I'm pretty sure can answer the questions the best. What we wanted to do here is to work with a different plastic waste stream, which is nonetheless a large one. It's textiles. If you look at the textiles we're wearing, most of these are made up of several different fibers. So usually you have cotton and polyester, or maybe polyamide and some elastan, which is a polyurethane-based fiber. And recycling that is quite hard. Even if you have a shirt which says 100% of polyester, like for football or for sports, even there are some other things inside because of the stitches and of the labels and all that. So recycling that is very, very challenging. It's a large waste stream. I think it's the 4th largest if you count it down what we produce as a waste. And so the question is how can we recycle that? We here look at exclusively at cotton polyester streams, where we have a high content of polyester and a lower content of cotton. That's one of the very, very widespread combinations. And after some initial sorting and shredding process, we then use a hydrolysis reactor. So, okay, here we have the animation. I clicked it through. Oh, sorry, that was a little bit too fast. So the concept is we take our broken old textiles. We do not take textiles which are still good for secondhand and stuff like that. We do a size reduction step. Then we use enzymes, which are basically biochemical catalysts. And with that, we break down the cellulose fiber to glucose solution, and the PET fibers are not very impressed with that. So we already checked that. And then we can separate it because one is a fiber, the other one is in solution. It's a rather nice process. And then we can back with the PET fibers, we can go back to polyester recycling, mechanical recycling as we know it. With the glucose solution, it can be used downstream. We do not tackle that in the project directly because our partner, one of our partners, Austrocell, they have a plant in Austria where they are producing bioethanol, and they will be capable of feeding that into. So the route is already there. It would need some cleaning steps before. But it is already established, so we don't need to do research on that. Where are we currently? We're currently in the upscaling of the process. So we have in our lab, you can see on the right-hand side, a setup where we have either 40 or 150 liter vessel for this hydrolysis with all the pumps and all the inline measurements we want to have to monitor the enzymatic degradation process. Also, one of my PhD students, she's doing a PhD on that stirring and chemical reaction part. So we also have the idea to use, let's say, soft sensors like the energy input of the stirrer to monitor the process, and we are capable of doing it in about 24 to 18 hours. It depends a little bit on the exact composition, but after 24 hours latest, we have managed to degrade the cellulose so we can wash it off, and then we get the fibers. And we even have demonstrated with our partners also in Turkey when we go from the textile back to granules, back to fibers, back to a textile again. So that is already in there. Also, the larger trials is running at Ostrocell. They have a pilot setup where we have a 1 cubic meter vessel where we can do larger trials to have, let's say, 100 kilos or even a little bit more of textile in that. So my last slide basically is here. You can see the geographical distribution. Maybe we should overlap the 3 projects and see if we cover whole of Europe. That would be quite interesting. But while others may have a little bit more a northern focus, we have a lot of partners in Spain and France and Italy. And you can see here all the partners and the approximate geographical distribution of the European countries. So with that, thanks a lot, and be happy to take your questions.